this video is on section 4.4, part 4, so the final section, the final part of section 4.4, and I'm calling it the integral of a rate of change and the integral as an accumulation function. We're going to talk about how those two things are related. So first off, I want to remind you on what the fundamental theorem of calculus says. So the fundamental theorem of calculus says that the definite integral of lowercase f of x from a to b is equal to capital F of b minus capital F of a, where capital F is the antiderivative of lowercase f. Right? When we integrate lowercase f, we get capital F, and if we take the derivative of capital F, it's equal to lowercase f. So this means that we can also rewrite the fundamental theorem of calculus using different function notation. So if we thought about integrating f prime, that means that the antiderivative of f prime would just be f. And therefore, the definite integral of f prime from a to b would be just f of b minus f of a. So we're going to think about integrating rates of change. And a common rate of change, when we're thinking about a physics application, would be like movement, an object moving through space. And the rate of change of an object's position is known as velocity, right? And we'll use v of t to represent velocity. And it's common to use s. I know I've mentioned this before to you guys. It's common to use s, but like we could use x of t, we could use whatever function name we want to represent the position function, but s of t is common. So that means that s prime of t is equal to v of t. So when we integrate our velocity function v of t from a to b, that's the same as integrating s prime of t. So integrating the derivative of the position function. So then when we apply fundamental theorem of calculus, we get s of b minus s of a. And let's think about what each part of that difference represents. So s of a would be an object's position at time a. S of b would be an object's position at time b. And if we're talking about on an interval from a to b, we could think of s of b as the ending position and s of a as the starting position. So if we're calculating that difference, so ending position minus starting position, what is that going to represent? That's going to represent the distance from the starting position to the ending position, or in other words, the object's displacement. That difference we also refer to as the net change. And I know you've heard me say this before. So it's the net change in the object's position on the interval from a to b, right? We've talked about net area when we first started talking about integrating definite integrals, especially whenever a function was maybe positive and negative on an interval that we are integrating, right? We had to take into account that negative area. So when we integrate the velocity function on an interval, that ends up calculating an object's net change in position, also known as the object's displacement. So like if you thought about having a particle, let's say just moving in a horizontal line, right? And the particle is going to left or right. Left would indicate negative velocity, would indicate that the particle is moving to the left. Positive velocity would indicate that the particle is moving to the right. So if as time is passing, the particle is going to the left, and then it's going to the right, and then to the left a little bit, but not so much, and then to the right again. Whenever you integrate the velocity function that would represent that particle's movement or that particle's velocity, you would end up calculating the particle's displacement. So its distance from its starting position and to its ending position. Different than if we were talking about total distance traveled, right? Total distance traveled would be adding up the magnitude of each distance. So like taking how far the particle travels to the left plus how far the particle travels to the right plus how far the particle travels to the left again, right? And adding up all of those positive distances, right? Okay, so we're going to have an example where we're going to actually calculate displacement and then also calculate distance traveled, and it's just a little bit different. So for another example, let's integrate an acceleration function. Let's integrate acceleration. So A of t, which is the rate of change of velocity, right? A of t is equal to the derivative of velocity. V prime is equal to A of t. So if we're integrating the acceleration function, that's the same as integrating v prime, and therefore applying fundamental theorem of calculus, we get v of b minus v of a, which is equal to the net change in the object's velocity from t equals to a to t equals to b. So calculate net change in whatever you think about what the quantity is that the antiderivative represents, and it represents the net change in that quantity. So for a more generalized statement, we can look to the net change theorem. So if f prime is the rate of change of quantity f of x, then the definite integral of f prime from a to b gives the total change or the net change of f of x on the interval from a to b. Okay, so let's look at some word problems here where we're going to be calculating net change of quantity. So this one is calculator active. I have my calculator here ready. A cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when T is equal to 0. Okay, so then the cup of coffee will start cooling off. So if the coffee's temperature is changing at a rate given in degrees Celsius per minute by R of T equals to negative e to the negative 0.1 T, approximate the coffee's temperature after 10 minutes. Okay, so we know that the cup of coffee is initially 90 degrees Celsius. And we want to figure out after 10 minutes, what the coffee's temperature is. So we're going to take that initial temperature of 90 degrees Celsius, and we're going to figure out what the net change is. To figure out what the net change is, we're going to integrate from 0 to 10 R of T, which I'll write it out as R of T, which R of T, we are given the rule is -7. We can actually pull that -7 out front if we want. And then e to the negative 0.1 T dt. And we're using dt because the independent variable is t. You don't know how to integrate this yet by hand, but this is calculator active, so we can get an approximation of what the net change in temperature would be, temperature of the coffee in degrees Celsius, by typing this into our calculator. So -7 times math, number 9 is f int, 0 to 10, and then e to the negative 0.1, and remember we have to type in x in our calculator as our independent variable. Okay, so the approximation that I get is negative 44.248, and that would be degrees Celsius. Okay, that wouldn't be the temperature, right? That wouldn't be the temperature at the 10-minute mark, but that tells me that the temperature decreased by 90 degrees. So another way to write this, and we're going to talk more about this when we talk about the definite integral as in writing accumulation functions, is another way to write this would have been to say, okay, well, 90 degrees plus the net change and then you could type, here you could also write that as 90 degrees and then minus 7 times the definite integral. You could have just typed that all in. So 90, so I'm just adding 90 to that value. And we get approximately 45.752 degrees Celsius. Sorry, so the cup of coffee, maybe I should make the statement that this video is being made because we are remote with the COVID outbreak. I apologize for my cough. Okay, so this means that the coffee's temperature after 10 minutes is approximately 45.752 degrees Celsius. So this would be the actual net change in temperature from 0 to 10 minutes. And then this is the actual temperature at 10 minutes or after 10 minutes. Which is what the question was asking. Okay, next example. An automobile accelerates from rest at 1 plus 3 root t miles per hour per second. Interesting units. For 9 seconds. And I understand why, because we want to measure our time in seconds here. So, okay, the automobile accelerates from rest at 1 plus 3 root t miles per hour per second. Okay, so this is our acceleration function. This is a of t. And we want to know what is the velocity after 9 seconds. Now, it's important to recognize that it says that the automobile accelerates from rest. So it goes from velocity being 0, and then accelerates based on that acceleration function. So this is going to allow us, in order to calculate the velocity after 9 seconds, that'll be the integral from 0 to 9 of 1 plus 3 root t, not 2, dt. And this one we can integrate by hand. So applying fundamental theorem of calculus, that would be t, and then this is 3t to the 1/2. So that'll be plus 3 times 1 over 1/2 plus 1 would be 3/2. T to the 3/2. 0 to 9. Okay, and then clean that up before I apply fundamental theorem of calculus. So that'll be t plus 2t to the 3/2. So then applying fundamental theorem of calculus, that'll be 9 plus 2 times 9 to the 3/2. And then it'll be minus 0. Okay, so simplifying that a little bit just because we can. So that'll be the square root of 9 is 3, and then 3 cubed would be 27 times 2 plus 9. Will be 63. And our units are for velocity, which will be miles per hour. So the velocity after 9 seconds, and that's because it's saying after 9 seconds, so that means from 0 to 9 seconds, the change in velocity from t equals to 0 to t equals to 9 is 63 miles per hour. So this also ends up being the actual velocity at 9 seconds. Okay, so we're given a graph that represents the velocity of a particle that's moving on the x-axis. And the particle starts at x equals to 2 whenever t is at equal to 0. So at time 0, we're not given units there. So at t equals to 0, oh, we are seconds, sorry, t is in seconds. At t equals to 0 seconds, the particle is in the position at x equals to 2. And then it's going to be moving, right? Whenever the velocity function is below the x-axis, that represents the particle moving to the left and then towards the negatives. And then whenever velocity is positive, that represents the particle moving to the right. So we want to find where the particle is at the end of the trip. Where is the particle at the end of the trip? Okay, so we have to look at the graph here. And it looks like the graph is only defined from t equals to 0 to t equals 7. So I'm assuming that t equals to 7 seconds is the end of the trip. Now, if we integrate our velocity function from 0 to 7, that's going to give us the displacement of the particle. However, the particle is not starting at the origin. We are given that the particle is starting at x equals to 2. So we need to take that into account here. I'm going to call our position function x of t. So this will be the particle's position at time t, where t is in seconds. Okay, we know that x of 0 is equal to 2 based on this statement. Okay, so that means that when we go to integrate, we're going to need to take into account x of 0 being equal to 2. So the particle will end up at whatever 2 plus the integral from 0 to 7 is of v of t. Okay, so from the definite integral from 0 to 7 will represent the particle's displacement. And then we're taking into account its initial position will be at 2. Okay, in order to evaluate this definite integral, we are going to have to use some geometric formulas. Okay, so we want to calculate what this area, well, that's going to be negative area, right? And then positive area and negative area. Okay, so from 0 to 1, that triangle is going to be negative, right? Negative area, I mean. So it'll be minus, what is that, 1/2 base times height would be 2. So we're going to end up subtracting 1. And then plus, we have a trapezoid. So 1/2. This side is a length of 4. This side is a length of 1, it looks like. And then the height is 2. And then we have some more negative area. So minus 1/2 base is 2, and then height is 1. Okay, and then simplifying that, there'll be 2 minus 1. What does that? No, the 2's will cancel. So we'll have 2 minus 1 plus 5 minus 1, which is 5. Okay, so the particle will end the trip at 5. So doesn't that mean that x of 7, right? If we integrate it from 0 to 7, that means that x of 7 is equal to 5. Oh, and it looks like meters. Looks like distance is being measured in meters. Okay. So total distance traveled by the particle would be, we'd want to add up, like, for the distance or the magnitude that the particle is going to the left, and then plus the magnitude of the distance of how far the particle is traveling to the right and then to the left. Okay. Sorry. So that means that we basically want to integrate from 0 to 7 the absolute value of our velocity function. Right? We want all of our negative areas to be positive. We're going to think about reflecting them over the x-axis, okay? So this represents distance traveled. So when you integrate the absolute value of the velocity function, that will end up representing total distance traveled over whatever the interval of time is. So in this case, that will be 1 plus 5 plus 1. So 7 meters. And then I wanted to put a textbook example on here just so that you could see an example of finding displacement and total distance traveled with an equation. You'll have some of these in your practice problems. I think I'm going to do this one and then go get a drink of water and then make a second video. Okay, so we are given that velocity in feet per second of a particle moving along a line is represented by this cubic polynomial, right? This third degree polynomial, v of t, where t is time in seconds. So what is the displacement of the particle on the time interval from 1 to 5. Well, that means that we're going to be integrating v of t from 1 to 5. Okay, this is one that we could do by hand. Okay, so I should have left more space for that. That's okay. Okay, so from 1 to 5, and then applying fundamental theorem of calculus. So, because I'm running out of space, maybe I will just use my calculator here. But you would do this evaluated at 5 minus that evaluated at 1. So we should end up with 32/3. Sorry, I should be going down here. I should follow what I tell you guys to do. I'm going to draw a line here and then put equals to 32/3, and the units for distance are feet. Okay, so the displacement of the particle on the interval from 1 to 5 seconds is 32/3 feet, or 10 2/3 feet. Okay, total distance traveled. So if we think back to the example from above, distance traveled, right, we saw is the integral of the absolute value of v of t. So integrating from 1 to 5, the absolute value of v of t. Well, how do we do that? How do we integrate? Well, one option is if you have a question that's calculator active, type in the absolute value of the function into your calculator. I can easily do that here. But if this were not a calculator active problem for some reason, what you could do is you could figure out on what intervals the function is positive and just integrate those, and then also on what intervals the function is negative, so that you can take the opposite of those integrals and then add those integrals up, because we have to integrate from 1 to 5. Now, one way that we could figure out, because there's different techniques you could use. I would need to use rational root theorem, I think, to factor this by hand. But since we are resourceful, I graphed this so that I could see what the x-intercepts are, right? So 1, 4, and 5 are the x-intercepts. And I can also, just from looking at the graph, see where our velocity function is negative and where it's positive. So it looks like from 1, okay, we're just integrating from 1 to 5. So it looks like from 1 to 4, our velocity function is already positive. So 1 to 4, it's already positive. And then it looks like from 4 to 5, it's negative. So we could take the opposite. We would want to go plus, and then take the opposite, which will just end up being minus the integral from 4 to 5. okay? Because the integral from 4 to 5 would be that negative area that we've talked about. And we want to end up adding the opposite of that value. Okay, so then it's two definite integrals. You could integrate by hand using fundamental theorem of calculus. Because this polynomial has so many terms, that would be pretty tedious. I'm just going to show you what each of those values would be. And again, you can type in the absolute value bars and just think about integrating the absolute value of your v of t function. That is also an option. Or if you wanted to type into the y equals your function and then call the function up in your integral using y bars, you could totally do that too. Especially if you know that you are going to be typing it into multiple integrals for some reason. dt dx. Okay. So did I type that in correctly? So I get 45/4, and then 4 to 5. I should have taken my own advice and typed into y equals. Okay, so then that ends up being minus -7/12, which ends up being 71/6. Our units will be feet for distance traveled. So again, you could type in the absolute value, or you could do this all by hand. Okay. And now I'm going to